Welcome to my presentation about direct wind energy-based water desalination, and specifically direct wind energy-based water desalination with reinforcement learning control for off-grid application. My name is David Keisar. I'm a PhD candidate at the Technion University in Israel, and this research is with collaboration with Professor Greenlaw David from the Technion. So let's dive in. We're going to start talking about wind pumps. So everyone knows the American multi-bladed wind pump, which is a highly reliable and widely proven wind pump. There's a large distance between the shaft from the ground, and this is why they are using reciprocating pumps. However, those pumps only have between 4 to 8% efficiency, pumping efficiency. And this is at low speeds. So at high speeds, they have only 1%, 2% efficiency, which makes them not really suitable if we want high pumping efficiency systems. So a few years ago, we thought about a concept. Maybe just use a vertical axis wind turbine connected to a pump to pump water. And apparently, there's almost no research about it, and specifically, there's no research about high-pressure vertical axis wind pumps. So we published research recently, as you can see, and this work is based on that work. So the high-pressure vertical axis wind pump is basically a wind turbine with a direct connection of the rotating shaft to a pump. We use a high pressure positive displacement pump, and it is really important for next steps you will see. The pump location is next to the ground. It's omnidirection to wind, so it's better suited for gusty and small scale systems. And specifically, we're using a vertical axis wind turbine, which is dynamic stall driven wind turbine. You can see a paper we published a year ago about this subject. And the advantages is that this turbine is highly aerodynamic, has high aerodynamic efficiency at small scales. It has a relatively flat max power peak, and it rotates very slowly. So it both creates low noise emissions, and there's a lower probability of bird strikes. So our main motivation comes from the water energy nexus, which is the relationship between water and energy. And the motivation is to develop a simple, small, sustainable, and efficient wind-driven desalination system. And specifically, a system that will be pure mechanical system with no electronics and whatsoever. And all the electricity generation and control will be the next step. We're going to talk about this also. So what is the integration problem? So the conventional solution is to create electricity out of wind energy by using wind turbines, meaning that we have sensors and we have controllers to give us the maximum energy we can take out of the wind. And then the desalination plant also has controllers and sensor in order to optimize the system. However, with a pure mechanical system, we don't have any controller, and we need to integrate several subsystems. In this case, we have a certain wind regime, and we have a wind turbine, a pump, and a desalination system that we need to integrate between them. Each one of them has a different efficiency curve, depending on its rotational speed, on the pressure, on the flow rate. So how can we maximize the desalination system outputs if we don't have any controller? So let's start with a basic calculation. We know that the energy that comes from the wind that the turbine gives to the shaft equals to the energy that the hydraulic power that the pump gets. It's the same shaft, so the power in is the power out. If we assume that the turbine efficiency function is not a function of Reynolds number because it's only a secondary parameter to the turbine efficiency function, and we're going to use a positive displacement pump, and we're going to assume that the pump efficiency is not a function of its RPM because it's also a secondary parameter to the pump efficiency function. We're going to get that the relationship between the power of the turbine and the hydraulic power is linear, and it's cubic to a function of the wind speed cubic. Meaning that if we get high efficiency at a certain wind speed, we're going to get the same high efficiency at all wind speeds. So if we can plan a system that will work efficiently at one point, it will work efficiently at all points. And this is our main motivation. So a more advanced theoretical modeling, we can see here a theoretical model of a turbine with a cross-section of 12.5 square meters at wind speed between 4 to 8 meters. And this is the dynamic stall-driven wind turbine power course. And we can see what is the maximum power points of the system at different wind speeds. And this is the maximum operating points, the maximum efficiency operating points. So we can plan a system that will work at 90% efficiency, or 90% maximum efficiency from the turbine, meaning almost the maximum efficiency we can take out of the wind with the specific turbine. And why don't we work here? This is because this equilibrium is non-stable, so we prefer to work at 90% maximum efficiency. So for the system, we get a certain pressure that changes with the wind speed and a certain volumetric flow rate. And if we want a system that will create, let's say, more pressure because the water is more saline than in other places, we can just change the pump, we change the system a bit, and we're still going to work at very high efficiency, but we will have higher pressure. So this is what's nice about the system. We can change the pressure at different wind speeds, but we won't affect the maximum efficiency of the system. So let's go over the schematic of the solution. We have a dynamic stall-driven wind turbine, and it's connected with a gear speed increaser to a high-pressure positive displacement saline water pump. The water goes through a pretreatment system, and they are pressurized to high pressure. And this high pressure brackish water or saline water goes through a reverse osmosis models that gives us clean water that goes through a post-treatment system and high pressure brine. And we can use the clean water for drinking or any other human uses. Or we can, let's say, take the high pressure brine and we can power a regeneration pump to pump the clean water in order to irrigate a field. Or we can just use a water tower or any other known solution in order to irrigate fields with less saline water, as we have, let's say, in the south of Israel. When we have a lot of wind, we have saline water in aquifers, and we want to irrigate the fields with sustainable energy. Another thing we can do is we can create electricity. So how can we create electricity? We just take the high pressure brine and spin a Pelton wheel, and then we can generate electricity out of the Pelton wheel and store it in batteries and use this electricity. And what's nice about the solution is that the same efficiency will remain, meaning that if we produce electricity out of the system, we won't affect the high efficiency of the system. And once we have electricity, we can use a spear and stepper motor and the solenoids in order to regulate the flow and the pressure, in order to create more electricity or to create a better flow in the desalination system, in order to have cleaner water, or in order to work at the maximum efficiency point. And we need a controller for it. So we said, maybe we're going to use deep reinforcement learning-based controller. Why should we work with a deep reinforcement learning-based controller? This is because the system always needs to adapt. With time, the aquifer becomes more saline, and the pressure needs to rise. And this controller can compensate a bit. and maybe one of the models wears off, or the pump or the Pelton wheel. So the system can always change a bit, and the controller can always adapt without the need for fine-tuning by a specialist. And this is our next step in the research. So the conventional solution, if we compare it to the conventional solution talks about creating electricity out of sun, out of wind, and then using the electricity as a medium to power desalination power plants. We can see for the wind, let's say in the Canary Island, the very famous research facility that research between wind and desalination system is using electricity as a medium in order to power the desalination system. So we have a wind turbine that creates electricity, and only then we have desalination system. And all these things have a lot of electrical converters and electrical panels and a lot of sensors that creates higher costs. So the advantages of such a system, of course, it's using a sustainable energy. It has very high efficiency. It produces electricity. However, the disadvantages, it must have a large minimum scale of a system, because you use so much electricity, electrical systems, and you must have a big enough wind turbine to create enough electricity in order to reduce the cost per gallon of clean water. So you need high capital investment in such systems. The distance from the community must be large, because the wind turbine create a lot of noise. They can hurt birds and any other winged creatures. They have a lot of complicated electronics, meaning that we must have technical support of people that have proficiency in such systems. Our solution, on the other hand, doesn't use all the electrical devices. So there's no need for a large minimum scale. You can still create a system which is only 1 meter square. So there's no need for high capital investment. There's no need for distance from the community, because the dynamic stall-driven wind turbine basically don't create any noise. It's much more safe to birds. There's no need for complicated electronics, and there's no need for technical support, because it's a pure mechanical system. So the people can maintain it if something happens. There's no need for a special electrical proficiency. We still use sustainable energy, which is wind energy. It has high efficiency, and if we want, we can produce as a byproduct electricity with the system. So the initial small experimental setup in our lab is a wind turbine with a 0.8 meter square cross-sectional area. And we have a lot of sensors and a lot of electronics in order to optimize the system. We use water treatment. Specifically, we use reverse osmosis fouling resistance brackish water membranes, several different ones, and pre and post treatment systems. We can produce electricity using the high pressure brine coming out of the nozzle. And we wrote reinforcement learning control algorithms in order to control the systems. And this is our next step. So the next steps is the evaluation of the pure mechanical system, which is the wind desalination system. Our preliminary results show that the maximum efficiency from wind is higher than 10%, meaning that the whole system is quite efficient. And this is only for a system that is less than 1 square meter in its cross section. Later on, we're going to evaluate the combination of desalination and electricity production, and then the possibility of reinforcement learning-based control system. And we're gonna also evaluate a wind desalination system which has a cross section of 3.5 square meters. We have both systems. We just want to finish the research, and then we can publish our all the results we get. So to summarize, our motivation is to develop a simple, small, sustainable, and efficient wind-driven desalination system. The system uses wind energy to desalinate and treat water for off-grid uses, both for agricultural uses and human uses. The basic idea is a mechanical integration of vertical axis wind turbine, positive displacement pump, and reverse osmosis desalination. Electricity generation can be easily integrated into the system with no efficiency loss. The system can be positioned in human habitat areas with minimal disturbance due to the low noise. Theoretical analysis and models promise high efficiency operation for a variety of wind speeds. And preliminary experimental setup also indicates high efficiency operation regime at small scales. Future steps includes an integration of reinforcement learning-based control system for everlong adaptation, and the system can be easily scaled. Thank you for listening. I hope you enjoy. I hope to meet each one of you face-to-face in our next conference, maybe in MIT or in any other place. And if you have any question, you can message me or you can message Professor Greenblatt. Thank you very much. Have a good week.